Hello dear students, I am Meghamala, working as an assistant professor from Electronics and Communication Department, IARE, Dundigal. And I am here to talk about language elements. So before we go forward, let me explain, or else let me recapitulate the previous class, what we have discussed. So in the previous class, we have discussed about the modeling styles. So model styles. So here we discussed in the last class about 4 different types of models, the styles. First one is behavioral. Second one is data flow. Third one is gate level. And the fourth one is structural level. So these are the 4 prominent modeling styles in the Verilog. So when it comes to the behavioral modeling, in this behavioral modeling, in order to write a program, we use a keyword called assign. We use a keyword called. So coming to the behavioral modeling. In order to write a program in this behavioral modeling, we are using a keyword called always. Always is a keyword which is used in the behavioral level of modeling. And when it comes to the data flow, in this data flow modeling, we are using a keyword called assign. Assign is a keyword where we are assigning the primitives to the particular module that we are considering. And coming to the gate level itself is a simple model where we are introducing the different various gates which are already present in the Verilog library. Like the prominent gates are the important gates that we had discussed in the earlier classes are AND, OR, XOR, NOR, etc. So using this gate level, different types of gates we can make use. And the last one is structural level. In this structural level, in order to write a program, we are using a keyword called wire. Why? Because in this structural modeling is nothing but it's a composition of numerous gates. It is a composition of many number of gates. So in order to connect each gate from each gate to another gate, we are using a keyword called wire, where we connect from one gate to the another gate. So here in this structural level, in the program, we are mentioning a keyword called wire. So these are the 4 basic modeling styles that we had discussed in the previous class, Verilog. Coming to today's topic. Today's topic is all about the language elements. So what is this language? In order to say that the constructs and the conventions, which are these two, the constructs and the conventions, they make up a software language. Software language is nothing but it is a language where the constructs and the conventions, are nothing but the basic keywords where we are using and their specifications. Okay. Next, Verilog has its own constructs and conventions. Verilog, as it is a case-sensitive language, Verilog language is a case-sensitive language, and in this language we are using, Verilog has its own constructions and as well as own conventions. Okay, own keywords, we can say in other words. And also, any source in Verilog is made up of number of ASCII characters. So in this Verilog, any source that you consider, that particular source that particular source is made up of number of ASCII characters. What is this ASCII? American Standard Code for International Interchange. American Standard Code for Information Interchange. It is American Standard Code for Information Interchange. So, any source in the Verilog is made up of number of ASCII characters. Okay. Coming to the next point, the characteristics are grouped into set referred as lexical tokens. These lexical tokens already we have discussed in the previous session. What are these lexical tokens? Lexical tokens are again categorized into 7 types. Okay, so the characters, the ASCII characters are grouped into set of lexical tokens, and the lexical tokens are, they can be single or else they can be a group of characters. Okay, so this lexical tokens, they could be of single group or else they could be of single or else they could be in a group of characters. So here are some lexical tokens that or else language elements that we see in the Verilog. So first come to the comments, identifiers, keywords, value set, delays or data types, memory elements, constants, parameters, and operators. Okay, so in detail we are going to discuss what are these lexical tokens and what kind of help what are these lexical tokens and how they are going to help us in order to write a program. Coming to the first one, it is a keyword. So what is a keyword? As I said you before, Verilog is a case sensitive language. As it is a case sensitive language, the keyword define the language constructs. So it is a keyword, one of the lexical token that we are considering, and this lexical tokens, it defines the language constructs. Okay, it signifies the activity either initiated or terminated. So this particular keyword, it just describes about the activity. Either it could be initiated or it could be terminated. Okay. Next, a programmer cannot use keyword for any other purpose than intended for. So here this is an important point to be remembered, where this point is talking about a programmer cannot use keyword unless and until it is meant to be used for. Okay, for general purpose the programmer cannot be used keyword wherever he wants to. Okay, but only for the purpose where it is intended for, where it is actually necessary, in that particular sense only the programmer can only use a keyword. So here in the example we have module, end module, begin, end, if, while. So these are the few keywords that we mention when we write the Verilog program. So when it comes to the module is nothing but it signifies the beginning of the module definition. So in the previous class also, in the module concept, I have explained what is a module. Okay, what is a module? Module consists of input ports, output ports, and in-out ports, isn't it? Input ports are entry ports which enter into the module. We consider the inputs, and the output ports are exit ports. Okay, which comes out of the module, and in-out ports, the combination of input and output ports. So when we write this particular Verilog program, in the Verilog program itself, we start with the module. Okay, we start with the module, and for suppose the module that the particular device, electronic device that you are considering is a gate, module and gate, and here comes the port list. This is already we have discussed, and you can consider this as a recapitulation. So when it comes to the module, it signifies the beginning of the definition. Module and gate. Okay, and gate, the module, the device, the circuit that you are considering is AND gate, and the port list. This port list consists of, first we have to mention the output ports, input ports, okay, and in-out ports. So here the module signifies the beginning of the module definition. And then the next one is end module. End module is nothing but it is basically the end of the module definition. End of the module. That means we are terminating the particular module. We are terminating the particular program with end module. We start with the module keyword and will end with the module, end module. So after module we have few statements. Input ports, output ports, or else register, and then we terminate this particular thing with the end module. Okay, so this is an end module is a keyword where this signifies the end of the module definition. And then begin is a keyword. It specifies or else it signifies the beginning of the block statement. So here we have few statements to be written, isn't it? Okay. So statements, we begin with the word keyword. That means here we begin. Begin, input, begin, input, A1, A2. Okay. Output, B1 or else C1, B1 for example. So here this begin, it signifies the beginning of the block statement, and end, it signifies end of the block statements. That means once we begin, we must end it, right? So here somewhere else, here we end the block statement. This is a statements regarding the particular block that you are considering. If it is an AND gate, the AND gate specifications would be written over here. So in order to write that block, we have to mention a keyword to begin, and to end up, we end up with the keyword end. Okay, this is all we see in the block statement. And coming to the if is nothing but it is a condition. It signifies a conditional activity to be checked, isn't it? In the C program also you see this kind of construct, right? If, while, do, while and so on. So the similar fashion in the Verilog also, the keyword if, it signifies a conditional activity. If itself is a word, it specifies the conditions of a particular statement. So the it signifies the conditional activity to be checked. And coming to the while, which is the last keyword, where it signifies the conditional activity to be carried out. Okay, if is a condition and while is this condition to be carried out, and also if this condition is terminating, then there itself it is well and fine. Otherwise, again it goes back to the loop continues. It goes back again to if, else if. Okay, else if. Again it comes to the while. So this is how the keywords will be mentioned in the Verilog program, and this is very important in order to write a program. So module, end module is the beginning of the module definition. End module is nothing but the termination of the module definition, and begin is nothing but it signifies the beginning of the block statement, and end is signifies the end of the block statement, and if is a condition activity to be checked, while is a significant, while which signifies or specifies the conditional activity to be carried out. Okay, this is all about a construct called keyword. Coming to the next construct, that is identifiers. What are these identifiers? Identifiers are nothing but any program requires block of statements or signals. So in order to write any program, the program will contain itself the block of statements and signals. Okay, so with name tags, identifiers. So in order to write a program, a particular program, that particular program, Verilog program, it contains a block of statements and also the signals. We represent the block of statement and signals as a name tags called identifiers. Next, it is always good to use identifiers related to the significance of variables, blocks and signals. So it is an easy way, and also it is a very important and easy to represent the signals and the block of statements using a name tags called identifiers. And all the characteristics of the alphabets or underscores can be used as first characters. So here in this identifiers, all the characteristics of the alphabets, we can use all the characteristics of the alphabets, and also we can use underscore. Alphabets and underscore, okay, can be used for the first characters. Next, subsequent characters can be of alphanumeric type, underscore, $sign. So the first foremost thing is we have to represent, or the first character should be alphabets or underscore, and the subsequent characters could be of alphanumeric. Okay, alphanumeric and underscore and $. These are the basic or the first characteristics. The first sign should be, the first character should be alphabets or underscore, and the subsequent characters should be, it can go for the alphanumeric, underscore or $. Okay, these are the identifiers, the basic identifiers. For example, here in this particular thing, he has given name, comma, underscore name, dot, name, comma, name 1, name, underscore dollar. So these are the identifiers. Here we could see dollar, we could see the alphanumeric, we could see the numerical number, and we could see the alphabetical number, and we could see the underscore. So these are the identifiers. And also name AA, not allowed as identifiers because of the blank. Name and A are represented as two different identifiers. So here if you see, here nowhere in this particular second sentence, nowhere we are observing any underscore, neither alphanumeric bits, neither alphanumeric bits, alphabets and dollar sign. Nothing is mentioned. It simply clearly says that name AA not allowed as identifiers because nowhere we are seeing any identifiers in this particular thing. Okay, coming to the second one, dollar name not allowed as identifier because of the presence of dollar as first characteristics. As I said you, the basic characteristics should be considered as alphabets or underscore, and then comes the alphanumeric. These are the secondary, where these are the primary or basic. So here dollar name, these are not allowed as identifiers. They are not allowed as identifiers because dollar has a first characteristic, and one underscore name is not allowed as identifiers where the number is a first one. Underscore name not allowed as identifier because the character is character at the rate, and A plus B not allowed as an identifier. So here, as these are the secondary identifiers, such that these are the secondary identifiers, but still they are mentioning at the first. So in this case, we are saying that they are not allowed to be identifiers. Only the first identifiers would be these underscore, or else it should be alphanumeric, or else it should be the alphabetical number, or else should be the dollar. Okay, and then next comes the primitive, and next comes and the subsequent characters could be alphanumeric, underscore, and all. These two are the important points to be remembered when you are writing a program using a construct called identifiers. Coming to the comments. So what are these comments? Comments, basically we all know what are the comments, right? So here in this particular Verilog language also, we have different types, or else there are ways to mention the comments. So comments can be inserted into the code for readability and documentation. So here in this particular in Verilog, we see the comments are inserted into the code for readability in order to read it easily, and also for the documentation purpose we are inserting the comment keywords. And two ways to write the comment. So there are two ways to write the comment. So first one is a one-line comment which starts with this, and a multiple line comment starts with like this and end with like this. So one-line comment we see with a slash, double slash. This is a well-known fact, right? The multiple comments is important. The multiple line comment, it starts with underscore and a star, right on a comment, and end with star and underscore, star and slash and star, comment, and end with star and slash. Okay. So, and for every star and slash. And coming to the multiple line comments cannot be nested. So a multiple line comment starts with slash, star, and ends up with star and slash. And the next one, multiple line comments cannot be nested. So here is an example they have given. A is equals to B and C, colon, double slash. This ID is one line comment. So here you see a double slash. So it means that it is a one line comment. And the second one, this is a multiple line comment. How it is a multiple line comment? Why? Because you see a slash and a star, you see a slash and a star, and you see a star and a slash. So it represents that it is a multi-line comment. And this is an illegal comment. Why it is an illegal comment? Why? Because the sentence starts with slash, star, and in between you see a slash and star, and in between you see a star and slash, and the last you see star and slash. Okay, the star and slash, the multiple lines are the star and slash, all these are repeated. Okay, so this is an illegal comment. And coming to the legal comment is starts with slash, star, ending up with a single line comment, and you are ending up with again, and this particular statement is ending up with a multi-line. So part we can say it is a legal comment. Okay, so this is one of the construct that you see in the program using how we are using this comments. Coming to the operators. So what are these operators? Operators are of three types. Okay, operators are of three types: unary, binary, and ternary. So what is a unary operator? Unary operator precedes the operand. Binary operator appears between two operands. The unary operator, it precedes the operand, whereas a binary operator, it appears between two operands. And ternary operator have two separate operators that separate three operands. Here you see ternary operator, it separates the operator that separates the three operands. These are the three operands, whereas binary, it appears between two operands, whereas unary operator precedes the operand. So here is an example. In this particular example, we can see A is equals to not B, and the statement goes like this: not is a unary operator, B is a operand, isn't it? So we see only one operator, that is not, and we see only one operator, one operand, that is B. Coming to the second one, A is equals to B and C. So here it is, and is a binary operator where B and C are the operand. So here in this binary operator, the operands are B and C. Whereas in unary operator, you see only one operand, that is B. Okay. And coming to the third one, ternary operator, A is equals to B, question mark, C, colon, D. So here, this is a ternary operator, B, C, D are the operands. You see B, C, D. B, C, D are the operands, and you see question mark and this one as a ternary operator. So this is how we represent in the Verilog program when it comes to the operators. So there are basically three operators: unary, binary, and ternary. Unary operator, it makes use of only one operand. Binary make use of two operands, and ternary make use of three operands. Okay. Coming to the number specification. So what does this number specifications talks about? There are two types of number specifications in Verilog. Okay, so what are those two types? One is sized and the second one is unsized. So what are the sized numbers? In detail, we'll discuss what are the sized numbers and how we are gonna specify this size numbers in the program. So these size numbers are nothing but they represent as size, base format, and number. There is some specifications how to represent this size numbers. So these are represented as size, base format, and number. Coming to the size, what is this size? Size is written only in decimal and specifies the number of bits in the number. So this size particularly, it specifies the number of bits in the number. So it could be of 7-bit number, 8-bit number, or 4-bit number, 2-bit number, like that. So it specifies the number of bits in the number. Next, legal base formats are decimal. So here there are base formats. So base formats, it could be hexadecimal, decimal, binary, and octal. These are the basic legal base formats. So base formats for binary it is 2, for decimal it is 10, okay, octal it is 8, and hexadecimal it is 16. So these are the binary, these are the base formats of our decimal, hexadecimal, binary and octal. Okay, so we now we come to know in size numbers we represent the size. Okay, the size is nothing but the number of bits. And base formats, what kind of base formats are you taking? It could be, as I said, your decimal, octal, hexadecimal or binary. And finally the number. Next, coming to this next point, the number is specified as consecutive digits from 0 to 9, A, B, C, D, E, F. Uppercase letters are legal for number specification. So here we are representing, the number can be represented in the consecutive digital forms from 0 to 9. Okay. And also the uppercase are legal for number specifications. For number specification, uppercase is used, that is A is equals to 10, B is equals to 11, like that. So these are uppercase letters are legal for the number specification. And coming to the example, he has mentioned here clearly 4-bit binary 1111. That is, this is a 4-bit binary number. Okay, this is a 4-bit 1, 2, 3, 4. 4-bit binary number. And coming to 12 HABC, this is 12-bit hexadecimal number. Okay, this is a hexadecimal number. Why it is an hexadecimal number? Hexadecimal number means here, see, more than 10 we see here, right? 12 HABC. We represent for more than 9. We represent in the uppercase letters, which is a legal form. Of number specification. That is A, B, C, D, E, F. So 12 HABC. This is a 12-bit of hexadecimal number. And coming to the 16-bit D255. This is a 16-bit decimal number system. D is a decimal number system, hexadecimal number, and it is a binary number. So this is how we represent the numbers in the sized number format. So the size number format consists of what? The size, base format, and the number. So the size could be the size is specified based on the number of bits that you are, or the number of bits in the number contains. And the base format is hexadecimal, binary, octal, okay, octal, and also the decimal. And the number is the number the number that you specify. So this is how we write the representation of the signed numbers. Coming to the unsigned numbers. What are these unsigned numbers? Unsigned numbers are the numbers that are specified without a base format. Okay, without any base format specification, and decimal numbers by default. So what is this base format? Base formats we see binary, octa, hexa, decimal. Isn't it? So these are the base format. So if the numbers which are not specified without any base format, then they are called as unsized numbers. Okay, and numbers that are written without a size, and also no base format, and also no size. There is no, that means we can't tell what kind of, or else how many number of bits that number is having. So there is no size at all, and there is no base format at all. And so the numbers that are written without a size specification have a default number of bits, at least 32 bits. So here in this unsized numbers, we see by default it has 32, at least 32 bits of information will be there in this unsized numbers. For example, 2, 3, 4, 5, 6. So if you observe this number, this is a 32-bit hexadecimal. Okay, 32-bit hexadecimal number. And in another form, we can write 32-bit octa form and 32-bit form. So the decimal number by default hexadecimal, octadecimal. So here we are saying that numbers are not specified without a base form. Specifications are hexadecimal numbers by default. By default, these unsigned numbers by default we can represent in the decimal format. How is by using this, how is by default hexadecimal in decimal format, right? So hexadecimal or octal numbers. Okay, this is how we represent the unsized numbers. The important point to be remembered is for sized and unsized numbers. For sized numbers, you see size, base format, and number. Whereas for unsized, there is no size, there is no base format to be considered. So this is the main difference between the sized and unsized formats. Coming to the next keyword or the next lexical token is X or Z values. What are these X or Z values? So Verilog has two symbols for unknown and high impedance values. So in the Verilog program, this Verilog, it has two symbols which are used for the unknown values X and the high impedance Z. Okay, so these are the important for modeling real circuits. So for the real circuits, the representation of X and Z, that is for unknown value, that is X, and high impedance Z value. So these are the two important for real circuits. Coming to an unknown value denoted by X. So unknown value is denoted by X and high impedance value is denoted by Z. Okay. So coming to the example, we discuss 12H12X. So here it is. This is a 12-bit. It is a 12-bit hexadecimal number and it has 4 LSB unknown. So 4 least significant bits. So here in this 12-bit of hexadecimal, there are 4 least significant bits are unknown bits. Well, coming to the 6 hexadecimal, it is the 6-bit hexa number. This is a 6-bit hexa number, whereas in the previous one, you see the 4 least significant bits. And coming to the 32-bit, it is simply a 32-bit high impedance number. So there is no representation. Here we are represented with hexa. Here also we are represented with hexa decimal. But here, nowhere we are representing either with hexadecimal or binary or octal. So what do we say? This is a high impedance number. So here in this 32-bit is a high impedance number. Why? Because here we did not mention anywhere the number specification. The base format specification has been has been not mentioned here in this particular example. So that's the reason we are simply mentioning 32-bit. So this is a 32-bit high impedance number. This is how we represent the unknown numbers and the high impedance numbers. So here the statements talk about an X or Z set 4 bits for a number in hexadecimal base. So here in this hexadecimal base, we see 4 bits. So that 4 bits are, it could be of like don't care or unknown or Z values, which sets for the 4 hexadecimal base. And 3 octal base means 1, 2, 3. Okay, we can divide 1, 2, 3, 0, 0, 1, 1, 0, 1, like that, 0, 1, 0, like that. But here in this hexa, we represent 0, 1, 1, 1, 1, 0, 1, 0, 0, 1, 0, 0, like this. This is hexadecimal base. Whereas octal, 3 bits, 0, 1, 1, 1, 0, 1, 0, 1, 0. So this is octal base. That is a 3-bit. It is a 4-bit. And 1 bit is binary base. Okay. For 1 bit, we represent binary. Binary base is 1 bit. So, if the MSB bit of a number is 0, X or Z, the number is automatically extended to fill MSB. You all know what is MSB and what is LSB. MSB is the most significant bit. LSB is the least significant bit. So, in order to extend the MSB bit, we can add or else the 0 can be added. Sometimes the unknown value X can be added. Sometimes Z can be added in order to fill the most significant bit properly. If you want, for suppose in examples, if you consider, there are times where we see only like this, this format. So here we left out with only one bit is missing. If you consider this hexadecimal, we divided the bits into 4 bits. But here you see only 3 bits. So in this particular, you can add up 0. Sometimes you can add up X. Sometimes you can add up like Z. Okay. These are the X or Z values which are important for the only to model the real circuits. So if MSB bit is 1, then it also 0 extended. So sometimes if it is 1, it can extend to 0. Like that. That means what? For suppose here you see only 3, but in few examples you may observe this all like this. Like this you may observe. So you can add up here 1, or else you can add up here 0, or you can add up here 0, or you can add up here 1. So here we can make use of this X or Z values. We can make use of X or Z values or else 0 in order to extend the MSB bit, the most significant bit. So these are the constraints that we see in the Verilog. And coming to the negative numbers. So what are these negative numbers? Negative numbers can be specified by putting a minus sign before a constant number. So this is a well-known fact saying that the negative numbers usually we specify with a minus before a constant number. Size constants are always positive. So in these negative numbers, we see the size constant is always a positive one. Okay, there's no limit or there's no restriction for this size constants. It could be always a positive one. It is illegal to have minus sign between base format and number. So as I said you, negative numbers are usually be specified with the symbol minus, but it is illegal to have minus between base format. That means what? Minus base format hexadecimal. That is minus 12, minus 16, or else like that. So this is illegal to have a minus sign between the base formats. Hexa, octa or binary. If you have any minus symbol in between, then it is not to be considered. For example, here you see minus 6D3. That is, it is a 8-bit negative number stored as 2's complement of 3. That is minus 6SDS. So this is minus 6. It is a 8-bit negative number. It is a 8-bit negative number stored as 2's complement of 3. 2's complement of 3. What is 3? You know, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So this is 0, 1, 2, 3. So what is 1's complement for this? 1's complement is? What is 1's complement? 0, 1. And again, if you add, if you make a 2's complement for this, you will get 0, 1, 0 like that, isn't it? So the 2's complement of 3 is minus 6 SDS, and this is used for performing signed integer math with 4D minus 2. That is illegal specification. So here this is a wrong way of specifying the signed integers with a minus in between. So if you see, this is a decimal. This is a decimal representation, 4-bit decimal number. This is a 4-bit. So this is a 4-bit decimal number. In between, you are specifying with minus 2. For 4-bit decimal number, you are specifying minus 2, which is illegal, which is wrong. So we cannot specify minus 2 in between. So that is what the second sentence is talking about. It is illegal to have minus sign between base format. This is a base format you are using if you are using any minus sign, and that is absolutely wrong. That is illegal to be mentioned. Coming to the underscore character and the question mark. Underscore and the question mark. So what does this underscore and question mark talks about? Underscore character is allowed anywhere in a number except the first character. So except the first character, anywhere in between numbers, you can allow the underscore character. You can allow it, but not in the first character. Underscore characters are allowed only to improve readability of numbers and are ignored by Verilog. So this underscore characteristics, they are allowed only to improve readability. Okay, the important point to be remembered here in this underscore, how to use this underscore and the question mark is, underscore characteristics is allowed anywhere in the number except the first character. That is important for except the first character. Here we cannot use the underscore. First character must not be used as underscore, but they are allowed only to improve the readability of number and are ignored by the Verilog. They are not that mandatory. Okay, they can ignored by the Verilog, but they cannot be used as a first element in the program. Next, a question mark is a Verilog HDL alternative for Z in the context of numbers. In the previous slide, we have discussed X and Z values, right? What is this X value? X value is a unknown value and Z value is a high impedance value. So here, this question mark can be replaced, or else it can be used as an alternative for Z in the context of number. That means what, we can make use of Z or else question mark. Anything, any way we can make use, and in place of Z we can make use of the question mark. For example, in this particular thing, you see 12-bit 1111. So it is an hexadecimal bit of 1111 underscore 4 zeros underscore 1010. 1010 is 10, 00 is 15. This is a 15. So this is a how we are using this underscore. As I said you, the underscore is not expected to be as a first character. So nowhere you see underscore at the first character. In between you can use. So the use of underlined character for readability, 4-bit of 10. So this is a 4-bit of 10, which is equals to 4-bit of 10 ZZ. As I said you, ZZ is nothing but it is a high impedance value. 4-bit of 4-bit decimal of high impedance value, which is equivalent to 4-bit of 10. So this is how we represent the underscore in between the numbers, but not as the first characteristic. Okay, this is all you will we can observe while writing the program while writing the Verilog program. This is one of the lexical token. So the in this negative numbers, the underscore and the question mark, how the underscore and question mark have been used, we have discussed. So in this particular presentation, for today's presentation, we have discussed what are the language elements that we use in the Verilog description. Okay, so we have discussed so many things, right? Comments, and we have discussed the signed and unsigned numbers, and we have discussed the modules, and so many things we have discussed so far. And this is like the end of the particular presentation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.